Welcome to Department of Collegiate and Technical Education. We're studying the subject Principles of Communication System, which is the fifth semester, Electronics Communication Engineering. In that one, Module 3, Chapter Noise, and Session 7, we are going to study now. So, as already we have studied about noise, introduction, short noise, thermal noise, white noise, and noise equivalent bandwidth, noise figure in the previous sessions. And basically, we are going towards noise in analog modulation. That is here also introduction receiver model, noise in double sideband suppressed carrier receivers, noise in AM receivers, threshold effect, noise in FM receivers, capture, FM threshold, how to reduce FM threshold reduction. These are all the things we have covered up. Now we are going to cover up pre-emphasis and de-emphasis in the FM system. So these are the table of contents, pre-emphasis and de-emphasis in the FM system. So noise in the analog modulation, this is thing, and pre-emphasis and de-emphasis in FM. So basically, the average noise power at the receiver output is given by the expression shown here in 6.1 equation, and average noise power at the output of FM receiver is given by is proportional to 1 by carrier power squared. That is, whenever we are increasing the carrier power, noise gets reduced, and this effect is nothing but a quieting effect. That means we are reducing the noise totally, and that effect is a quieting effect. And the output to signal to noise ratio, that is, since Ps is equal to Kf squared P, that is output signal to noise ratio SNR output is given by output power by output noise, output signal power by output noise power, that is given by 3a squared Kf squared P by 2 n naught omega cube, that is signal to noise ratio of FM. Transmitted power of an FM waveform Pt is equal to a squared by 2. For a signal to noise ratio baseband, that is transmitted power divided by n naught omega is equal to beta is equal to kf mp by omega. So signal to noise ratio FM is given by the expression what is shown here. That is 3 kf squared p by omega squared s. Signal to noise, there is nothing but signal to noise ratio into baseband. So this equation is valid when the carrier power is large compared to the noise power, because whenever the carrier power is large, the noise power, if it is a smaller quantity, then the output signal from the transmitter to receiver it will reach without any noise effect. Otherwise, the noise effect will be more. The threshold effect. The FM detector exhibits a more pronounced threshold effect than an AM envelope detector. The threshold point occurs when signal power is 10 times noise power. So you can see there is an expression shown here which we have discussed earlier also. Below the threshold, the FM receiver breaks and it significantly deteriorated, and this can be analyzed using the thing. So which we have discussed earlier also. Here we can see the qualitative decision. As the noise changes randomly, the point P wanders around P2 in the previous figure, and here also the high signal to noise ratio change of angle is small, and low signal noise ratio P1 occasionally sweeps around the region, resulting in the changes of 2 in the short time. So how to improve the signal to noise ratio? You can see that power spectral density of the noise at the detector output a square of the frequency. That means you can see the first figure here, the noise noise is less at the center and noise power is less at the center. At the minus omega and plus omega, the noise is at the peak level. But here the signal ratio, the signal, that is power spectral density at minus omega and plus omega, it's almost minimum, and at the center it is peak. So totally the outer edge we are not able to use. The power spectral density of a typical message typically rolls off at around 6 dB per decade, and to increase signal to noise ratio of FM, use a low pass filter to cut off the high frequencies at the output, and message is attenuated too, but not very satisfactory. So to avoid this one, we are going to use pre-emphasis and de-emphasis, and the message remains unchanged and high frequency components of noise are suppressed by using this. How is this? We'll have a look of the block diagram. So here in the pre-emphasis and de-emphasis, you can see the block diagram shows that m of t is given to the pre-emphasis filter and it is fed to the FM transmitter, and in the channel we have the noise and it comes to the FM receiver. At the receiver end we have a de-emphasis filter and at the output we have a message plus noise. So how it is been covered up, we'll have a look here. So, for this, a more satisfactory approach to the efficient utilization of the allowed frequency band is based upon the use of pre-emphasis in the transmitter and de-emphasis in the receiver. This is the thing what you are going to discuss. And in this method, we artificially emphasize the high frequency components of the message signal prior to the modulation at the transmitter end. That is, high frequency components we are emphasizing here at the transmitter, and therefore before the noise is introduced in the receiver. So in the effect, low frequency and high frequency portions of the power spectral density of the message are equalized in such a way that message fully occupies the frequency band allotted to it. Thus, at the discriminator output, that is the receiver, it performs an inverse operation by de-emphasizing the high frequency components so as to restore the original signal power distribution of the message. In such a process, the high frequency components of noise at the discriminator output, that is at the receiver, is also reduced, thereby effectively increasing the output signal to noise ratio of the system. Such a pre-emphasis and de-emphasis process is widely used in the commercial FM radio transmission and reception. So here, in order to produce an undistorted version of the original message at the receiver output, the pre-emphasized filter is in the transmitter and de-emphasized filter is in the receiver and must ideally have a transfer function that are inverse to each other, so that it increases the signal at the transmitter so that the noise whichever is coming at a low frequency or in case some high frequency also is eliminated at the receiving end using a low pass filter, and the high frequency what you are given at the transmitter is de-emphasized, that means removed at the receiving end, so that only we are effectively using the message signal. So here we can see that HPF used to artificially emphasize the high frequency components of the message prior to modulation, hence before noise it is introduced, and HDEF used to de-emphasize the high frequency components at the receiver and restore the original power spectral density of the message signal. So therefore, these two are, that is pre-emphasis and de-emphasis, are used widely as of now, that is the FM transmission. So this can improve the output signal to noise ratio around 13 decibels. So Dolby noise reduction uses an analogous free emphasis technique to reduce the effects of noise, that is hissing noise in the audio tape recording, and is also concentrated on high frequency. So improvement factor, that is assumed as an ideal pair of pre-emphasis and de-emphasis filters are shown here. The power spectral power to signal on signal noise of the PSF of the noise at the output of de-emphasis filter is shown here. The average power of noise with de-emphasis and the use improvement factor is also shown here. That is PN without pre-emphasis and PN with pre-emphasis, pre or de-emphasis is also shown here. And the example circuits for pre-emphasis filter and de-emphasis filter are shown here and the relevant expressions. So comparisons of analog systems, that is assumptions, single tone modulation, we have this MT is equal to AC cos 2 pi FCT, and message bandwidth is omega is equal to FM. For the AM system, mu is equal to 1, and for FM system, beta is pi. This is only just a comparison. And conclusions. The full AM, the signal noise ratio performance is 4.8 dB worse than the baseband system, and the transmission bandwidth is BT is equal to 2 omega. And double sideband, the signal noise performance is identical to the baseband system, and transmission bandwidth is BT is equal to 2 omega. And SS single sideband, the signal to noise ratio performance is again identical, but the transmission bandwidth is only BT is equal to omega. And FM, the signal to noise ratio performance is 15.7 dB, better than a baseband system, and the transmission bandwidth is BT is equal to 2 beta plus 1 omega is equal to 12 omega. With the pre-emphasis and de-emphasis, the signal to noise ratio performance is increased by about 13 dB with the same transmission bandwidth. So